Michael Levin, Andrei Karpathy, the idea of 0 to 1 innovation. Is Tesla a 0 to 1 innovation? What's the intelligence that Tesla is trying to create? And how does adaptive intelligence, like Michael Levin's doing research in his biology lab, how does that relate to software 2.0 and what Tesla is doing? I want to discuss these concepts and focus on really the intelligence part. Let's start with trying to understand what is intelligence and then go from there and try to arch ourselves into what Tesla's doing. There was the Tesla AI Day yesterday, on Friday. Today's Sunday. It's October 2nd. So the AI Day is past. I will do a formal review of the AI Day, but I can already say from what I've started to see and listen and hear and read about it, I unfortunately wasn't invited, but it looks like Tesla is doing definitely a hybrid between the game theoretic approach that I would like to see them play more, where they have a system that adapts to the environment in a sort of risk-reward reinforcement learning type of way, and then they have a lot of optimization and even some mapping of the environment and things like that. So I want to discuss all these things and then bring in Michael Levin, which is, it's one of these things, it could be coincidence or not, but Lex Friedman had him on. He actually introduced him as a friend that was introduced by Andrei Karpathy. So I think there's a line, there's a lineage there. And Andrei, who left Tesla, is apparently more interested now in biology because it teaches you about intelligence, and there's a fruitful back and forth here. This is Not Even Wrong podcast. It's October 2nd, 2022. This is Krimdelko. It's a Sunday. There's no update for the year. We're down 35.1%. The market's down 26.3%. We're underperforming by 8.8%. Tesla just announced their quarterly numbers. They produced 365,000 cars, which is in line with expectations. They only delivered 342,000. That's way less than expected. So the stock will probably take a bit of a hit. The reason they didn't deliver as much is it's all driven by logistics constraints, on top of the fact that they had a push towards the end of the quarter, and then they didn't want to overpay for a delivery. So that's their narrative. I think the street will take it with a grain of salt. The street will be afraid that this could be a demand slowdown, particularly a demand pocket maybe in China. So until the earnings call, I guess clarity will not be there, and that will weigh on the stock. But now let's talk about this concept of intelligence, which is a big, I would say it's a big theme, of course, in many ways. Tesla just had their AI Day, and we've been doing a lot of work on reinforcement learning here at Orange Capital Partners. We've said on many occasions that we believe that Tesla should go down that route, end-to-end learning, use more of a mu-zero approach. And what I saw so far from the Tesla AI Day is actually, I think they're sort of tiptoeing their way towards a mu-zero approach. For example, there's a search tree where when there was a presentation where the gentleman that is running that particular module at Tesla, the planning module, is explaining how the car is negotiating with the environment in a sort of a microsecond cadence about what to do. So this reminds me very much of the Monte Carlo search that DeepMind is doing. So there's probably a convergence there of AI practitioners, particularly those who are delivering real intelligent systems that are interacting with physical systems, of which I would say Tesla is by far the leader in the world right now. Those are converging towards this mix of representative models, so supervised and unsupervised learning. There's some reinforcement learning, although they didn't use the word, but there could be some reward function involved. The gentleman said, I think it was Ashok, actually the head of the AI, or the co-head together with Milan. He said that there is one situation that we will punish if the car did that, so the car won't do it. And there's another situation that we will not punish or be rewarding positively. So that sounded to me a little bit like reinforcement learning, but they didn't use the word, and I think there's probably some political an ego and vanity type of reasons why they're not using that. But let's put that aside. Unfortunately, I wasn't invited, so I can't talk about these things other than just conjecturing. But what's important here is the following. We have a very adaptive system. That's the key. Karpathy, who was with Tesla for many years, coined the term software 2.0. What he meant with that is that we have a system where we define the parameters and then the algorithm gets shaped by consuming data. And instead of us explicitly programming outcomes in a von Neumann type way, we are using more of a data flow model. And I think this goes back to the new paradigm in compute, where we go from the von Neumann architecture actually to data flow architecture. That is a whole different conversation again. I want to focus on Michael Levin here. This is the sort of the big title of this particular episode is really Michael Levin's work in biology, where he explicitly thinks about questions such as, where does intelligence stop and physics start? Or what does it mean, just physics? In other words, if I take a human and I strip the human down, I will at some point end up with physics. First, I will end up with, I'll go from a human with a me and an I towards molecules and cells. And then at some point, it'll be physics. It'll be covalent combinations. It will be ionic combination and all that kind of stuff. So he's asking those questions. And by asking those questions in the nature of Popper, of course, he's creating lots of problems. For example, this is one problem. Okay, where does the I, the human, the consciousness end, and where does physics start? It opens up a lot of new problems. And there's just one beautiful example where he says that they took a cell and they isolated or they took a cell system and they isolated the cells that were supposed to become membranes or skin cells, and they let them go free in a petri dish, and then those cells started to act in a very different way. They didn't become skin cells, they become something else. I think they call them Zen robots or something. It doesn't matter. The point here is that there seems to be an intrinsic will or an intrinsic drive that systems, cells have, and that they are able to express when they're alone, and then they're not able to express when they're not alone. When they're not alone, when they're in the confine of another system of cells or an organism, then they have to abide to certain other rules. For example, when they're in the system of, I forgot if it was human or some sort of animal, they turn into skin cells. So why is that also important? Because we're talking here about flexible adaptation. We're talking about the ability to solve problems with different approaches, which is one of the definitions of intelligence. And I hope you can see where this is really nicely relating to the Tesla problem. What is Tesla building? A robot, a car, and then also a humanoid robot that hopefully will be able to adapt to the environment in a very flexible way. How do you do that? Well, you have to find ways to program that thing. Right now, we don't have better ways. But if you really take the biology at its core, it is a system of programs. It is a system of algorithms. And those algorithms and programs, they are executing against this overarching optimization problem, which is solve problems within the context of constantly being offered different data from the environment and often very little data. This is also something that Jeff Hinton is talking about and is trying to take home, which is that the human brain has, or the human system, not just the brain, has very little data and lots of parameters. And the way our algorithms work in AI right now is the other way around. Lots of data and relatively little parameters. So how do we bridge that gap? Now, Tesla is trying to solve it by structuring the problem into vision and planning. The vision side seems to be solved to the point where it's satisfactory because they haven't spoken about it a lot, and also their head Karpathy left. So that makes me think that the focus now is on the planning. And there, again, there was a lot of mu zero type intelligence being shared with the audience. In other words, I think the one thing that stuck into my mind is the fact that, okay, here's just a few tidbits from the presentation. For example, again, this gentleman, I think he was an Indian guy, but not Ashok, somebody else. He said that they're able to predict, so they're looking at the objects that the vehicle is exposed to, and then they're predicting first, second, third, and fourth derivative kinetic parameters. So that means that a car is coming at a certain the first derivative would be, so the first is the position, and then the velocity and the acceleration, and then the change of acceleration. So all of those things are being computed, so the car can negotiate with that object in a sort of microsecond type cadence. This is, to me, looks a lot like some kind of game theoretic reinforcement-ish type learning. So I think Tesla's on a good path there. And it's very encouraging to see that. To me, this was my biggest curiosity when it comes to this particular AI day. I wanted to know, okay, what kind of approaches are they using? What kind of models? And I think the answer is they are actually going towards a mu-zero approach, or at least they're sort of in that realm, and that is incredibly encouraging. I think Tesla is by far the leader when it comes to physical AI. Now let me talk a little about Michael Levin. Why did I use him as an inspiration for this episode? Well, it's kind of related, right? You have this question. What is intelligence? You have the question of where does intelligence start? Where does physics start? Where does physics end? And where does intelligence start? And Levin has some very interesting viewpoints on that. I think, if you ask me, it comes from the point that just he's looking at things differently. This is a nice example of when people start looking at things from a different perspective, they come out with different answers. You know, it's like data. The truth is theory law, and data is theory law, and like you can't just say this is it. It always depends where do I look, which angle do I look from. And that's why it's so important also. I think that's the purpose of this podcast, is to give people a sense for what it feels like to run a hedge fund. And I cannot emphasize enough how important it is to read, how important it is to go to academic seminars, to read, to go to presentations such as the AI Day if you're invited. If not, then you just listen to it. And the reason for all these things is that it gives us different angles to look at a problem and come up with different answers. And that is incredibly useful for a hedge fund manager, because we are, I would say, one of the ultimate forms of intelligence, that we continuously have to adapt to the environment, and we're being continuously judged by the market. In other words, we can't really afford to make too many mistakes, otherwise we die. So we really are a physical intelligence that is using money as a measurement of success, and that is what the hedge fund business is all about. So Michael Levin has this, I think, beautiful perspective on biology, where he's trying to say, where does intelligence stop? Where does physics stop? What is just physics? What do all these things mean? And he, I think, comes up with very interesting observations. One of them is that Zen robot thing I spoke about. He also talks about the ability to adapt with very little data. And the reason biology has come up with that is because biology is always under incredible time constraint. Biology doesn't have a lot of time to react to the environment, because there just isn't that much time. And there are also mistakes when they're made. In other words, it's better to make mistakes and then progress through natural selection than to wait and do it the right way. This is a big lesson for, I think, anybody who's been in any kind of school system and has complained about why do they always put time pressure on me? Well, because that's kind of how nature works. You got to be fast. You got to come up with solutions fast. Even at Tesla, if you look at the people there, they're all good-looking, healthy-looking people, because I think their brains are fast. Everything there is fast. And speed on its own has advantages beyond just getting fast to market and all that stuff. What speed does, it makes you it calibrates you to make decisions with little data. So then you, by definition, start over parameterizing things. And I think that's what Tesla is doing in their car system. It's over parameterized. There's like 4 levels of degrees of kinetic information, for example, by object. So that, of course, with all these parameters, then you get to the problem of a blow up of action space potentials. And that's why they have this Monte Carlo search tree, where they search through all the possible negotiations and then negotiate, let's say, a left turn that the car has to take. Back to Michael Levin. What does Michael Levin say about biology? Well, he says that biology has found a way to code information in a way that it's incredibly adaptable to the environment. Now, his approach is what's called bioelectricity. So I would say if he would be somebody who would not necessarily believe that everything is encoded in the genome. In fact, most of the action in biology is happening with the information that is being translated back and forth between all the different players, the cells, the subparticles in the cells, the electrons, and all of that stuff. Now, how that works, of course, that's very difficult. But he said another very interesting thing. He said that if we try to micromanage biology to the point where we go all the way down to the genome, that's actually very difficult, and the side effects are very difficult. It would be much more useful if we could find some emergent characteristics of the system and then influence them. Now, what does that mean? Now, this is just on a side note for our CRISPR side of things, that we probably are going to find better approaches in medicine and life science if we can look at the cellular pathways, but then hopefully find emergent factors. If let's say we have a certain sequence of amino acids that fold into certain proteins, we find certain expressions that those proteins are either good at or bad at, and then we can influence them. So because we have this view now into the stack of biology, hopefully we can do more first principles approaches, but we don't necessarily have to go and change the genome. So the genome editing side of things could maybe be a bit put on the back burner, at least when it comes to practical applications, maybe not so much when it comes to research and development. So to summarize, I think Michael Levin's conversation was very inspiring because Levin talks about plasticity, he talks about adaptation, flexibility, regenerative medicine, regenerative materials. Imagine a humanoid robot that falls down and regenerates itself because it has the ability to do that. Now, Levin talks about one other interesting paper that he's about to publish, and that is, imagine if you built, let's say, a Lego tower out of Legos versus you build a Lego tower out of trained dogs. Now, to build a Lego tower out of trained dogs, that's obviously very hard. But once you assume you could do that, you would have a system that can regenerate itself. And that made me think that, imagine if you had a system that is, let's say, a humanoid robot that is built out of subcomponents that are trained to execute certain functions, then if that humanoid robot falls and damages itself, maybe those subcomponents could regenerate themselves. So this is a research area that's very exciting. I don't know if Tesla should be working on that right now, but it's very exciting. It just makes you think fundamentally about what is intelligence, what does it mean to encode information and execute against problems. And I think I want to finish this episode with what a working definition of intelligence. It's solving a problem when you're given different parameters. So in other words, you can solve the problem of not falling down while hiking up a mountain or going downstairs or running on ice. You still solve the same problem, which is not falling down, and that is what intelligence is.